lab 1 where I said don't go past this point, you may have noticed that attempting to create a user on Cloud9 costs Cloud9 to ask you for a credit card, and that's kind of not cool. So it turns out that the way you use Cloud9 would basically be within their free account service or whatever. So you could just put in a credit card and they would never charge you. But I don't really want you guys to have to do that. So right now I'm looking at an alternative, and it looks like it's okay. So what we're going to do is we're going to do lab 1 and lab 2 when we do lab 2. And at some point, lab 1 will be updated to reflect the different IDE that we're going to use. So an IDE is an integrated development environment. And Cloud9 is one such IDE. It's also a web-based integrated development environment, which means that you can use a web page to do it instead of doing it on some other program on your computer. So for that reason, when you have the new alternative, I think it's going to be code anywhere. You'll be able to use that, and you'll set that up as part of lab 2. But I will let you know when lab 1 is ready, and I'll send you an email saying, hey, go ahead and finish the rest of lab 1, and we'll just pick up the pieces with lab 2. If you have a problem with it, what you expect, then with lab 2, we're just going to make sure that you have your environment set up. You may have received an email regarding your Bitbucket account that a repository was shared with you, or that you now have administrative privileges for a Bitbucket repository. Yeah. That repository is going to hold all of your work in CSE2, and it's a way of storing that data. And we're going to talk more about what a Bitbucket and GitHub, or just in general, a Git repository does. You've probably heard of Git repositories, but we should talk about it more. Okay, so what we're going to cover today and tomorrow begins the sort of meat of the material in CSE2. So I don't want you to think that the material that we discussed in the first lectures, the first 2 lectures, is not the sort of thing that I might decide to ask you about on the exam. I expect you to understand all of those ideas, and I will ask about those questions. But they don't seem like they fall into the category that we're talking about. In the beginning of the class, it said there were 5 categories of things that you would learn, like assignment being the first one. And this is the beginning of that first category. But I don't want you to think that everything before that was, not the sort of thing that you need to know. Those things were the sort of things that are so important that you should have them at the beginning of your notebook and think about them every time you open your notebooks. But this begins the first important topic, and that's assignment. So assignment is a concept that happens in all programming languages, and it's a very important concept because it is very similar to the way a processor works. Assignment is the way that we store data in a particular place. Now, I'm going to talk about some mathematical ideas before we get into actual assignment, and that's so that we can have a basis for thinking about interesting problems that we can work on this with. But then we're going to talk about assignments and the consequences of assignment, like data types and arithmetic. Okay, so the example that I want you to think about, and the example that I want you to become familiar enough to answer questions about, is the base 10 number system and other number systems in other bases. So the base 10 number system is the number system that we all use, and it's a series of symbols to represent a number, and that series of symbols is described by a particular character that represents a multiple of a power of 10. And that's a really long way of saying that, we describe the number 84,953 as actually a sum of a series of multiples of powers of 10. But you can all see how that works, right? You can see how 84,953 is a sum of 8 times 10 to the 4 plus 4 times 10 to the 3 plus 9 times 10 to the 2 plus 5 times 10 to the 1 plus 3 times 10 to the 0. That concept should be obvious. Now, that concept doesn't have to apply to powers of 10. And I think many of you probably had number systems and numbering concept in different bases. But in computer science, we frequently deal with numbers in different bases because we have to operate with hardware constraints. And hardware constraints work best with numbers in different systems. So let's break down what we have in the base 10 number system and translate that to what we have in other base number systems. So we have a series of symbols. That series of symbols, we're all familiar with, 0 through 9. And each position of the sequence of symbols that we have here, 8, 4, 9, 5, 3, refers to a specific power of 10. And you can't skip one of these positions, right? I can't represent 84,903 by saying 8493. I have to have a 0 where that 5 is, otherwise it doesn't have that meaning anymore, right? So this ordering of symbols is very, very controlled. Now, I know this sort of thing seems obvious, but the second we change this power of 10, everybody's going to feel weird about it, right? So I want you to abstract what you know about the base 10 number system into these ideas and then translate them into other numbering systems. So the base 2 numbering system is what's used most in computing. And the reason why it's used most in computing is because when we have transistors indicate a voltage that is either high or low. And because it's easy to distinguish between high and low and not maybe different levels of voltage, then it's much better to have numbering systems that are just ones and zeros, highs or lows. And when I have a base 2 number system, that number system works exactly the same way as my base 10 number system, but it works with a different set of symbols. So we know that binary numbers have 2 symbols, zeros and ones, and that each digit position in the number that I have here represents a power of 2. And in computing, we also have a series of other numbering systems that we use. The octal numbering system, where every number is represented with a series of symbols from 0 through 7, and each digit represents a power of 8. And these things seem unusual, but it seems like it makes sense that I can describe this number here as a series of multiples of powers of 8s, just like the base 10 number system is a sum of a set of multiples of powers of 10s. So it seems like I can construct other numbering systems like this. But the second I have to think about arithmetic in some other base, we know that's when things get weird, right? If I give you a base 8 number and another base 8 number, figuring out how you do arithmetic on that gets a little bit unusual, and it's something that I want you guys to begin thinking about. Yes? And what's your name?
Patrice.
Patrice.
So I'm just a little bit confused. What is the, purpose of using different bases? Is it just different programs use different ones?
So when I have a computing system that is only working in terms of ones and zeros, in particular, if the way that it represents a number is 0 or 1, then I have to figure out how I'm going to wire that system so that it will actually make an addition. So at the second lowest level on a processor, the lowest level you can imagine just being a series of connections between resistors and transistors and things like this. One step above that, you have groups of transistors that are called adders or multipliers. And they're literally groups of little circuits that if you put in the voltages for a certain number, or 2 certain numbers, then you'll get a number out. And they're really simple because they don't handle multi-digit base 2 numbers. They only handle 1 digit of a base 2 number. And you add a multi-digit base 2 number together with a series of adders. And there's actually like a carry thing that actually carries the carryover bit. So if you want to actually figure out what the series of voltages will be on that series of adders, then you would need to do base 2 numbering. Now, that's the example for base 2. Octal has a completely different explanation. Octal has to do with the way that we store bytes in computers, and the base 16 number system, hexadecimal, is another numbering system that's convenient because of the way we store data in groups of essentially 16 bits. And hexadecimal is the first especially weird base number because numbering system because it has way more symbols than we're used to. So remember that the base 10 numbering system had 10 symbols. The base 2 numbering system had 2 symbols. The octal numbering system had 8 symbols. The hexadecimal system logically has 16 symbols, but we're not used to numbers that have more than 10 symbols in them. So where do those other numbers come from? One logical way to steal those symbols is to add A, B, C, D, E, F to the numbering system. So the meaning of these symbols is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So using these symbols, we can put them together as powers of 16 with a number like this, A5, F2C. And when I translate that, that will literally be 10 to the 16 to the 10 times 16 to the 4th, plus 5 times 16 to the 3rd, plus 15 times 16 to the 2nd, and so on and so on. Just like the numbers you saw are comfortable individual multiples of powers of 10 that we've seen before. Now, the reason why I'm telling you about these number systems is because I'm going to use it to exercise your ability to do assignments and other things in Java, and arithmetic and other things. So that means that I will need you to understand how you can do arithmetic with hexadecimal numbers, or how you can do arithmetic with octal numbers, and so on. So when you see a number that's represented as a series of digits, performing multiplication, addition, subtraction on those things can be a little bit challenging because those calculations will have to be modified for the numbering system. And we'll see about that in a few weeks when that comes up. It will come up before the first exam, but you'll see how this works. But just to give you an overview of your expectations, expect that you will need to know how to code a translation between a hexadecimal number to a decimal number, or from a hexadecimal number to an octal number, or an octal number to a binary number. To be able to translate it that way requires some special work that you're not used to, but it will require you to think abstractly about this, and I want you to understand this system because it will help you exercise your general understanding of how Java works on numbers and stores data. So let's think about how exactly we convert numbers to and from different bases. So how many people here know how to convert numbers from one base to another? Good, good. And how many people have seen it before, but maybe they don't remember? Okay, a lot. That's awesome. So the way that we're going to perform that conversion is the standard way, but we're going to break it down into the way that we would write a piece of software to do that. So remember, from our first lecture, we had a picture of a program that had inputs and it had outputs, right? So anytime we design a program, we need to design that program in terms of inputs and outputs. So the inputs, in this case, is the string of symbols. And we have to call it a string of symbols because it could be a hexadecimal number, right? The hexadecimal number has letters in it, so it's not really a number anymore, it's a string of symbols. And we know the number, that's the base of the input value that we want to convert. And we also know the base for the output, which is the base of the number that we want to convert this to. So those are our three inputs: the input base, the input number, and the output base. And the output that we want is the number in base 2. In other words, expressing the the number in the right symbols for base 2 to be equal in value to the number in base 1. Okay? Okay, so the way that we will do this is we're first going to transform whatever that first number is into base 10. And then we're going to transform that value in base 10 into the same value in the second base, the output base that we want to generate. And then we're going to print out the transformed number. Okay, so there are maybe more direct ways to convert bases for certain pairs of bases, but this is a general way that we can do it. When we put this all together, this process of having a defined input, defined output, and a series of steps is what we call an algorithm. And the examples that I showed you in the first lecture, you know, with the lemon garlic chicken recipe or whatever, is exactly a variation of this. This is exactly how we describe software. You know, when you guys are at your Google internship interview, your Facebook internship interview, they ask you to describe an algorithm. You need to say, well, the output will be this, the input will be this, the steps that are going to take are this, 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 and this. That's exactly how you describe how an algorithm works. Okay, so notice that when we describe the input and output, we describe it in a certain way. Now, the way I described it kind of required me to go this way, but now I'm going to highlight why I'm describing it in this way. So when I have inputs, I have names for those inputs. So I'm going to call that string of symbols that we're going to convert number 1. And I'm going to call the base for the input number base 1, and the base for the output number, I'm going to call that base 2. Those are just names for values because we're not converting just one number. We're converting any arbitrary number in any arbitrary base that comes into this algorithm into any other arbitrary base that is requested by the input. Right? So rather than referring to these things as specific values, these are variables. Just like you guys used in math, X, Y, and Z, in computer science, we refer to variables with specific names. And in particular, we have a name for that kind of name, and it's called an identifier. An identifier is a name that a variable has, and a variable is something that is holding data that we're going to use. In this case, our input variables. Okay, so when I store things in a variable, I can store all sorts of different things. So in Java, we have this syntax where we use the name of a variable, and we use a special character, equals sign, and we have the value that we want to store in that variable. And this equals sign, I want to sort of redefine in your heads right now. So you guys have 15 to 20 years of experience in mathematics. And in mathematics, the equal sign is commutative. You can take something on the right and something on the left, and you can flip it to the other side of the equal sign, and that's the same statement, right? The equal sign is not the same thing as the thing that I'm showing you here. In software, the equal sign is called the assignment operator. And the reason why it's called the assignment operator is because it is not commutative and it is not an equal sign. What the assignment operator does is it takes the thing on the right of the assignment operator and it stores it into the variable on the left of the assignment operator. And it never goes the other way around. You can't have $3,456,215 over here equals annual revenue. That doesn't work. That's going to result in an error that Java tells you doesn't compile. And the reason why that is because assignment is not equality. Assignment is assignment, and we store things by putting the thing on the right into the variable on the left. And this is a concept that exists in all programming languages. Sometimes the assignment operator, it isn't an equal sign, sometimes it's an arrow. But assignment is always moving the thing on the right, the thing on the left. And I'm harping on this in part because I frequently see people on their first exam saying, oh, it's the equal sign. I can have the thing on the left stored in the thing on the right, and it's the equal sign. It goes both ways. It doesn't go both ways. Okay. Yes. Your name is?
Greg. How do you tell whenever you want to, how do you know when to put, Frank on the right side and my name on the left side? How do you know when to differentiate and when to do that?
Well, the thing on the left side is always the recipient. So whatever you have on the left side, it's the container that's holding the data. And I don't know if I just said left or right. The thing on the left side is the container that holds the data. The thing on the right side is the data. Now sometimes the thing on the right side is also a container that holds data, and you want to take what is in there and put it into the thing on the left. That's okay. But just remember, it's always the thing on the right being stored into the thing on the left. Yes, your name?
My name is Hannah. Can you just repeat what you called the equal sign that you said an assignment is something?
Yeah, the equal sign is called the assignment operator. Good. Okay, so I can store lots of different things. I can store numbers, I can store dollars, I can store decimal values like pi 3.14. I can store strings like sentences or any list of characters. I can store lots of different things in variables. And in Java, we have this special property called type, which means that a variable can hold only certain kinds of data. And we'll get to that later. But in other languages, we have variables that can hold data from multiple different types. Yes?
I'm Olivia, and isn't pi already stored in certain programs?
That's a great question. So pi is indeed stored in certain programs and in certain languages. It's called a constant. We generally don't assume that it's stored, just from the most abstract programming perspective. And sometimes we want to use a specific decimal precision value of pi that might be different from the one that's stored normally. But frequently pi is available. And in fact, in Java, pi is stored as a constant to many decimal precision. So it's probably better to use that. This is simply my example so that they could think of a decimal that everybody knows. Great. Okay, so every time I introduce a new programming construct to Java, I'm going to show you the different steps for using that construct. And I've actually showed you how to use a variable in the first lecture, just with that tip calculator. But I'm going to abstract that for you here so that you always follow these steps. And the reason why I always want you to follow these steps is that it's really easy, especially for using variables, to do these steps in the wrong order. So what I mean by in the right order or the wrong order is that a program is a list of commands. You'll remember from the tip calculator that we first said that the result is equal to the total times the tip. And then we return the result. It's a list of commands that happens from the top downwards. And if you have things in the wrong order, in other words, you have something that happens above something else or before something else, then the computer doesn't know how to do that, how to run those commands. So let's see what these three steps are in the order that they have to occur. So the first thing that has to happen for a variable is called variable declaration. When I declare a variable, I'm simply telling the computer that this is the identifier for the variable, and this is the type for the variable. In other words, I'm saying to the computer, hold me some space in your memory that stores this kind of data, this type of data, and the name of this thing that I want to store, or this space that I want you to hold for me, call it this, give it this identifier. Great.
What would be an example of that? Like, what would you do before, like, my name equals Frank or something like that?
So an example of this would be like int annual revenue. Well, okay, annual revenue is not an integer. So int high score is equal to this would be an example of that, where I said, store me an integer. call it high score, and the value I want to store there is 214 billion, whatever.
And that's a variable declaration.
And that's a very, that was a very assignment and
Oh, that's all of them.
that's all.
Okay.
But here, let's go through the steps specifically. So first we declare, and then we assign, which we actually take a value and we store it in that variable. And then we can access that variable later. We can get that stored value out of the variable. So these three steps have to happen in order, otherwise you'll have a problem. Okay, so let's look at an example of variable declaration. That's happening in this line here that's highlighted in yellow. And it says float result. And this is real Java here. This is completely formal and I'm not leaving anything out. What this says is create me some space in memory that is sufficient to hold a floating point value and call that space in memory for me result. So that later on when I refer to results, I'm referring to that space in memory that I just asked you to store for me. Now, I need to tell the computer to store that space for me before I use it because otherwise it's not going to be prepared to give me space that it doesn't know about. So that's why declaration always happens first. The next step is assignment, right? Variable assignment. When I assign to a variable, I'm storing data from some other source into that variable. So in this case, it could be the tip calculator, and I take the product of the total times the tip, which is some number. In this case, it's some floating point number, because the total is some decimal value with dollars and cents, and the tip is some decimal value with dollars and cents. We multiply the two together. I'm sorry, the tip is not dollars and cents, the tip is some fraction. We multiply the two together, and we store the resulting value into results. We use the assignment operator to perform variable assignment. So here we're literally taking that value and storing it into that space in memory. And then finally, when we want to access the data that's in results, we're going to return it in this case, but other times we might want to print out that data, or we might want to use that data in some other calculation. So if I said like float my value is equal to result plus 5, the fact that result occurs to the right of the equal sign is an access to that variable. It's getting the value in that variable out and using it for something. So this code here implies that I have a variable called total and another variable called tip. Those are two variables that, when they occur to the right of the assignment operator, I'm accessing the data in those variables. I'm getting that data out and I'm doing something with them, in this case multiplying it. In other cases it could be something else. Great.
So would you have to make total and tip before you make this code to make it work? Oh.
Yes, you would have to make total and tip, and you would have to declare and assign them before you access them here in that middle line. Hannah.
So even if you were saying like int result equals blah blah blah, you still have to do the float beforehand to declare it, or does it int declare that you have?
Well,
numbers?
you would use float or int.
Okay.
In this case, float is a floating point number. It's short for integer. And there are other types that we'll learn about also. Remember, stop me at any time if you have questions. I want to deal with all of the issues that come up as they come up.
Does floating point number just mean decimals?
Floating point number just means that there's a decimal value. So an integer value has no value after the decimal point. It has no decimal point. It's just an integer. And then a float stands for a floating point number, which has values after the decimal point. And it's distinguished, I should say, the float is distinguished from an integer, not only because it has values at the decimal point, but because it's able to represent very large values and very small values, whereas integer can only represent integer numbers. So we'll talk a little bit more about data representations later, but there's a reason why those two things are very different. And in particular, Java has to reserve different kinds of memory for you, or differently allocated memory for you to distinguish between integers and floats. Okay, so as Greg pointed out, there were some shortcomings to the code that I showed you earlier. That's the fact that I had not declared total, and tip before. So if we really had everything in the whole program, then we would first declare results, then we would declare total, and then we assign some value to total, then we would declare tip and assign some value to tip, and then we would perform the calculation total times tip and store that into result, and then we would return the result. Yes, Andrea?
I'm on, so when you declare variables, you have to declare all of the ones you're going to declare and then go to the next step? So the result doesn't have to be right before result goes to like.
That's a great question. So Anna's question was when you declare, when you're using a variable, you declare all of them before you use them. That's true, and it doesn't, and as you pointed out, it doesn't have to occur immediately before you use it. So the important thing is the order and not the exact position. So as long as my declarations occur before I assign, as long as my declaration occurs before I assign, and as long as my assignment occurs before I access, then Java will have no problem with it. So here I'm declaring results as a floating point value, and here I'm declaring total as a floating point value, and I'm assigning something to total. Now, I could have said float total, float results, like swapping the order of these two lines, and that wouldn't have been a problem because I'm still declaring before I'm assigning. But just because I wrote it this way, it's occurring in this order.
Why can't you?
Go ahead.
Why can't you write float tip after you assign total?
Why can't I?
Why does all the float lines happen first?
Oh, that's a great question. So why don't all the assignments happen first? There's nothing that's stopping me from writing all the assignments first. So that still obeys the ordering. And in particular, there are some old programming languages like Fortran that actually require that all the declarations happen at the very beginning because they actually allocated all the memory in the very beginning and would not allocate memory after that.
So it's just for each variable, so as long as result happens before result, because it doesn't matter what's in
That's right. That's right. No more questions?
No, she answered it, that's her point.
Okay. Your question?
Yeah, could you put float result after tip equals 1.5?
Yes, you could. The question is, could you put float results, the top line here, over here underneath tip equals 0.15? And the answer is yes. Because float result is never accessed and never assigned, until this line here. It can occur as late as the line after tip equals 0.15. So that's a great question. And when you think about these things, it's important to, I realize that you're all getting familiar with these ideas right now. It's important to understand what variations might occur. So when you're coding your own thing, you'll need to examine how might my code be breaking these rules to make sure that you're not breaking them. And you can see again the sort of thing that we talked about the first time around, that you might not know what the problem is in your code until you've found the problem. And that's exactly what might happen here. You might not realize that something's out of order until you've realized, oh, that's the thing that's out of order, and you moved it. And you know that can lead you to not knowing how long it's going to take to finish something. So this is an important concept here, that order matters, and thinking about how order is correct or incorrect is a really important part of assessing the accuracy of your program. Yeah.
Do you not have to access all the variables that you declared or assigned?
Excellent questions. You do not have to access or even assign any variable that you declare. So you could just declare, I could declare like int extra and just never do anything with it. And that's totally okay.
Would it save anything?
It would not save anything. And some compilers would actually realize that you don't need to have it. So the machine code that they generate might not actually include it, but it doesn't result in any change in the way your software would behave.
So what does that accessing actually do?
So accessing actually gets the value that was stored in a variable out and uses it for something. So here, when we say result is equal to total times tip, we're accessing the variable total and we're accessing the variable tip in order to get their values out to perform the multiplication. So here, without assigning a value to tip here, and without assigning a value to total, then total and tip cannot be accessed because there's nothing in it. So because we've assigned them first, we can now access total and tip, and therefore calculate this multiplication.
And when do you have to write return result or return total?
So we have to write return results because at the very end we want to get the output.
Oh,
And what return does, that return command says, okay, the output is this. Access this variable and make it the output. All great questions. Yes?
I'm a lady, and I was wondering what the difference between float and int is.
Great question. So the difference between a float and an int I'll show you all the types later. But the difference between a float and an int is that a float has decimal values. In other words, it has 0.1, 0.01, 0.001 values after the decimal point. Whereas integers do not have decimal values. Yes?
So if you were not to add decimal points when you write down your code, would that result in a logic error?
What's your name?
Christian.
Christian, sorry.
Oh, is it optional?
So that's a great question. So Christian's question is if he were to not add values after the decimal point in the assignment of total and tip, would that result in a problem? And the answer is it does not result in a problem because Java recognizes that the whole number can be converted into a floating point number by adding 0.00. However, if result and total happen to be integers, and you attempted to assign an integer into a floating point value, if you attempted to assign a floating point value into the integer that was hypothetically total, then that variable does not store the right kind of data to hold that floating point value, and that would be a logic error. So what I'm saying is that anytime you have a different type, you can't store it into the same variable. The only exception here is that Java can compensate for some kinds of variation. So it can compensate for adding 0.00 at the end of your integer, but it can't figure out how to store those decimal values into a non-integer. And we'll talk about all of those things later, but that's an excellent point, realizing that you can't necessarily store everything. Okay, so we talked about how order matters in the series of commands that you provide to your Java code. So a syntactically correct tip calculator here on the left, what we just saw, differs from the syntactically incorrect tip calculator here on the right, where we do things out of order. So here you can see that I'm assigning to a variable that has not been declared, because above this line I don't see the variable total declared anywhere. Same thing is true for here for a tip. I'm declaring everything after I assign it, which doesn't work. I have to always declare first and then assign. And my accesses are I guess they can be okay, but the error is coming from declaration after assignment. Okay. All right, so as many of you noticed, there's different kinds of inputs. And I want to formalize that idea right now. So I've already sort of told you about the idea of type. So let's think about how we translate that from qualitative kind of idea into specific things in Java. This is really, really important, not just from the idea that, okay, variables hold a certain kind of data, but also in the way that we solve problems. And I want to take even a further step back here and tell you something about the way this course will work and the way engineering really works. And that is that engineers solve problems. And we solve problems that are described to us in some sort of language. In this class, it will be English. But when something is described to us in some language, the person describing it to you may not be an engineer. And when that person describes it to you in regular English, layman's English, you have to figure out what their meanings are in that English. And sometimes that can mean creating new things to satisfy exactly what they mean. And sometimes that just means figuring out how you can translate what they're referring to into something that you can implement in Java. So a constant challenge in this course will be reading a description of a problem. Write me code that does this, where there are implications in that English, where there are underlying assumptions in that English, where you still need to produce the correct kind of code, understanding those assumptions and implications. So one thing that frequently comes up when people first sort of get introduced to engineering is they say, oh, well, you didn't tell me to do exactly that. We're not teaching you to do exactly what somebody tells you. We're teaching you to be able to translate what they say and figure out what they mean. And in that regard, this class can come off as an English class in some of its extreme cases. So if you go and look at some of the exams for this class, there are questions that describe the kind of code that you need to write in paragraphs, like pretty long paragraphs. And understanding exactly what those paragraphs mean and translating them into actual code is a process of problem solving and language interpretation that requires really detailed understanding of what people mean in English. And that's a difficult challenge for everybody because you guys aren't used to doing that. I want to tell you about that now so that you guys are all prepared for that coming. Because it will come. And we'll have to talk about that when it comes up, probably after the first exam. So, zooming back into what we're referring to here, we need to translate what people are referring to in terms of number one, base 1, and base 2 into specific values. And in this case, these translate into rather specific values. So this is useful for our simple example of the base calculator. So as I said before, variables have to have a type in Java. And the reason why they have to have a type is because Java stores a particular amount of memory for each variable that it has. And different types require different amounts of memory. And also, Java records the type of a variable so that it can error check your code. Because if you attempt to write code that is illogical from the type perspective, then Java can tell you, hey, that thing that you're trying to do, I think it's an error because it doesn't seem to make sense. So for example, if I had a language that didn't care about the types that I stored in different variables, it would let me do things like add car plus 3. And it's not even clear what that means, right? If I have a bunch of characters and I want to add a number to it, it's not clear what could ever be meant by that. So that's the sort of thing that Java can highlight to the programmer saying, you might have a bug here because it doesn't seem like you might have intended to do this. And that's really useful. Having typed languages is really useful because it helps us avoid mistakes that might be really difficult to dig out. If you have a really long piece of code with hundreds of different variables in it and lots of different arithmetic operations, if at some point some variable that ends up holding a string like car and some other variable that ends up holding a number like 3 get added together, it'd be great if Java just said, hey, on that line, you're adding two things that are of different types, and that can't happen, that's weird. That's way better than having to trace through that whole program and being like, okay, well, car might have gone into this variable, and 3 went into this variable, and then it went over here, and it got added to this. And like tracing through that whole program to find out, oh wait, at this point we added those two together, that's where it blew up. Like the fact that type checking occurs in Java actually saves you hundreds and hundreds of hours before you even write the code, and that's an amazing feature of Java.
Oh, what's the difference between a type and a kind?
There's no difference. Types and kind. Kind is my colloquial definition of a type. Yes.
I'm sure that if you had assigned car as a variable to equals 3, would it still crash if then you did car as 3?
If I assign car to a variable that equaled 3,
Yes, like if you made car a variable that equals 3 before,
Yes, so if car was not the string, if car was actually a variable name, then, and it was a variable of type integer, then I could add it to the number 3, and that wouldn't give me a problem. And incidentally, I should say that this is not an assignment operator here. This is just me showing you what would happen. Assignment operators always have things right. But yes, there's a difference between a variable name and things that occur in quotes, which are literally strings of characters. Great.
So to get car to be like a variable, so you could add to three, what would you have to add so that like it was a variable? Like how would you make it a variable?
So there's a variable type called a string that holds literally lists of characters. So I could store car into a string variable. But if I wanted to get this to actually say, if I wanted this to produce a new string equal to CAR3, I could actually create another string that held the character 3 and add those two things together. So that can be done in Java, and that wouldn't result in a crash or a problem that Java would give you, because Java would realize you're adding two strings together, and adding two strings together in Java is okay.
Could you add an integer to a float?
Yes, you can. You can add an integer to a float only because Java will recognize that there are different types and recognize that you can convert an integer into a float before you add the two floats together. So technically speaking, and this is getting into arithmetic that I didn't want to talk about just yet, but technically speaking, anytime you operate on two different variables or values, they must be the same type. And an alternative is that you can convert one of those things to be equal to the other thing. Now, you can't always convert the two things to be equal. You can't always convert 3 into a string or a car into a number. And in those cases, Java will give you a crash. But that's getting into some details that I want to address later. For now, the important thing to understand is we have to have types that describe our variables. And when we operate on variables of different types, Java can tell us that is an error. Okay, so here in our syntactically correct tip calculator, you'll see that we're declaring the particular type that's going to be stored in each variable, in this case floats. And when we declare, remember that we always declare the variable type, like float, and then the identifier results, and it's always followed by a semicolon to indicate the end of that command. So anytime we declare, it always has at least two words. The first word is the type, and the second word is the identifier, and it's always followed by a semicolon. So any other way will not correctly declare this variable. There are some shorthand ways that are different, but this is the most basic way to declare a variable. Another important thing to know is that variable declarations have to be unique. So when I declare a variable, it has to have a specific name. That name is sensitive to capitalization. And you can't have another variable of the same name, even if that variable has a different type. They all have to have different names. And the reason why that is because otherwise Java will not know what you're referring to. And having variables of even similar names is a great way to confuse yourself, remembering what your variables are. So forcing variables to be different is helpful for both the programmer and the programmer. Okay, so what is the list of types that we're working with? The list of types that we're working with is basically these 6, and there's a few other types that are in the book that you should be aware of. But we will essentially work with only these types. So what are these types? These are the types that come with Java, so that's why they're called primitive types. They're called primitive because we build other things from the primitive types. And with the exception of string, which is primitive but not exactly that primitive, they all are they don't have any internal components to them. String is a little bit special because string also has a number of methods that come with strings that help you do cool things with strings. And that's why it's capitalized, whereas everything else is lowercase. Okay, so what we have are integers, floats, doubles, booleans, chars, and strings. So we've talked about integers and floats. Integers are integers, but they don't have values after the decimal point. Floats have values after the decimal point. Doubles are essentially floating point values with additional space after the decimal point in order to store more accuracy. Doubles are the same as floats essentially, except that there's twice as much memory, hence the name double. And that allows them to store more numbers before or after the decimal point in order to more precisely describe things. So it's the difference between describing, fractions like 0.25, 0.00015, and describing things like 10 to the negative 2. Okay, so a Boolean, which we'll talk about later, is a special value that stores only true or false. And we'll use those a little bit later. Chars are variables that store only a single letter. So A, B, C, D, E, F. And strings are lists of chars. Okay, so we talked about variable assignment. One thing before we break for today, there are shortcuts for declaration, assignment, and access, and that allows us to compress things. So here we've declared results, and then over here we've stored the value. We can declare results as we store values as we assign values to results by declaring it to the left of the assignment. Okay, so we'll talk about math operations next time. We're tending to run out of time in the lectures because of questions, which is fine, but you are still responsible for these slides, so be sure to review the rest of the slides and ask questions.